Chemistry. This is part 2 of 7.02, Unstable Isotopes. And I did get cut off a little bit at the end one. Sorry, I wasn't watching my 15-minute mark. But basically I was saying that the residual strong force, you can think of it as a force within a force. So it's the force keeping the quarks together inside the neutron and keeping the nearby protons or neutrons near it as well. And so here's a picture just kind of showing that the balanced forces within the nucleus. So the protons want to get away from each other, right? That's the purple. But an equally strong force, it's an equal force because the arrows are drawn the same size. An equally strong force is the strong force, and the residual strong force, the force of the quarks holding everything together. And the reason they call it the strong force is because it is the strongest force in the universe. For example, gravity. Gravity is a force. Gravity, as we know, causes everything to fall down to the earth, right? Everything is attracted to the center of the earth because of the Earth's mass. So gravity affects everything. We all know how strong gravity is. Gravity is very, very weak compared to the strong force. Yeah, stop for a second. The fact that everything is pulled down to the earth, that's nothing. That's really weak. That's a weak force compared to the strength of the force inside the nucleus of every single atom. The only difference is gravity can act a very long ways away. Gravity keeps the moon going around the earth. The strong force, even though it's extremely strong, is extremely short. It only acts within a nucleus of an atom. So at this point, you might be thinking to yourself, well, what about electrons? What are they made of? Well, as far as we know, electrons aren't made of anything else, and they are called leptons, and they don't have to do with holding the nucleus together. So they do exhibit a weak nuclear attraction, but really the quarks are what hold everything together as far as the nucleus goes. So if you're starting to think to yourself, okay, so yeah, it holds everything together, but what else does it have to do with everyday life? Well, it's used a lot in medicine, which we're going to talk about coming up in future lessons. They use it for power, like in Monticello, Minnesota, there's a nuclear power plant. And of course, it's used in nuclear explosions like the nuclear bomb. So again, you can hit pause and read this, but you don't have to add it to your notes. It's going to be coming up in future lessons. And so what we're going to be talking about next is radioactivity. So radioactivity is caused by the decay or the breaking apart of a nucleus. It occurs when an unstable nucleus or nuclei loses protons or neutrons. So we're going to talk a little bit yet in this lesson about radioactivity. So changes in the nucleus give off radiation that leaves the atom. So parts fly out of the nucleus. You have learned about the structure of the nucleus and the forces holding it together. So the strong force and the residual or leftover strong force of the quarks that are inside protons and neutrons. In many nuclei, an imbalance exists. So it's not perfectly balanced. And this imbalance exists between the forces holding the nucleus together and those that would tear it apart. So remember here in this picture I said, oh, all the forces are equal. Well, not all the time. So these nuclei with unequal forces are unstable, and they undergo a spontaneous or an instant change where particles and energy are lost. This is called radioactivity. So in the rest of this lesson, we're going to talk about different types of radioactivity. So here's what you need to write down. Radioactivity. The decay, and when we say decay, we mean breaking apart of an unstable atomic nucleus. And this happens when there's too many protons, not enough neutrons, and it's followed by the release of radiation. So make sure you add that to your note as a vocab word. So what's radioactivity? You've probably heard of it, like on the news or in books. And it has to do with nuclear bombs, dirty bombs, nuclear power plants, or perhaps in science fiction where a dangerous radiation harms starship crews, or a radioactive insect bite creates a superhero. Spider-Man, Spider-Man, doing whatever a spider can, right? So radiation can be harmful, but it can also be harnessed for useful purposes. So what exactly is radioactivity? It's the decay or breaking down of the unstable atomic nucleus followed by the release of radiation. So radiation can be a particle or energy. So you know what? Let's add that to our definition here. So radiation is a particle or energy. So what makes a nucleus stable or unstable? The stability or instability of a nucleus is related to the structure of the nucleus, so the quarks, and the balance of the forces that hold it together, so the quarks again, versus those that tend to make it fly apart, the fact that all protons are positive. So again, we want them to be balanced, but if they're not balanced, then they're going to move apart. And if you'd like, you can hit pause and read this, but basically the idea is if you have too many neutrons, too many protons, one or the other, you have problems. So elements 84 and larger are unstable. So if we look at our periodic table, so we're looking at 84 and higher, so the elements that are there, and the elements, careful now, not here in the lanthanide series, because remember, those go right here. So those are 57 to 70. But the bottom row, the actinide series, so uranium, okay, this bottom row which goes down here, these are unstable. So elements 84 and bigger are unstable. They decay or break down into more stable nuclei by getting rid of pieces and or energy. And we call these pieces and or energy that is released radiation. And so when we say that it gets to a more stable nuclei, it is making a new element. Why? Because we changed the number of what? Protons. So if you have a different number of protons, you have a different element. So again, make sure you have all this written down. And then this next part you don't have to write down yet. Radioactivity decaying atoms release particles or energy. All right, so when you have uranium, pieces fall off. Okay, and there's specific pieces that fall off, and those specific pieces are one of these three. You have an alpha emission, which is a helium nucleus, which is really just 2 protons and 2 neutrons. And this often gets released from a large nucleus. So uranium will spit out a helium nucleus. Uranium can also spit out a beta emission. This is the second type. A beta emission is a high-speed electron or positron, an anti-electron, from the nucleus, not from the orbitals. And if you're thinking, wait a minute, there are no electrons in the nucleus. You're right. But yet, during radioactive decay, an electron can be formed and spit out, and it's called a beta particle. Okay, this is crazy stuff. Or you can have gamma emission. Gamma emission is energy. This is an electromagnetic wave. Now, electromagnetic waves, so let's talk just for a second about what electromagnetic waves are. So examples that you've heard of, obviously, microwaves, right? And there's infrared rays, which are heat. The visible rays. The visible waves are the rays of color that we can see. The rainbow, red, orange, yellow, green, blue, indigo, violet. That's what we can see. There's ultraviolet, like you hear of UV, rays from the sun. There's X-rays. And then there's gamma rays. We don't talk a lot about those in everyday life, but those are the type of electromagnetic waves which are released from the atoms. So another electromagnetic wave that you obviously know about are radio waves. And it has to do with the size. And so they have these pictures here just so you have an idea of how big they are. So X-rays, we're talking the size of atoms. UV, we can't see. They're too small. Visible is still crazy small, but that's what we can see. And then the waves get bigger. Radio waves can be as large as skyscrapers. In fact, there are radio waves that are as big as the Earth. Okay, so it just kind of gives an idea of how big the waves are. So the type of electromagnetic waves are not microwaves, not rays that are visible, light that we can see, not radio waves, not heat waves, but gamma rays. Gamma rays are the type of electromagnetic wave given off when a nucleus of an unstable atom decays. So these are like your three choices. And now this picture, they're showing that a piece of paper can stop an alpha particle. But a beta particle will go through a piece of paper, but something like aluminum foil will stop it. Gamma rays goes through paper, through aluminum foil, through you, which is why these scientists that we talked about at the beginning, a lot of them died because of the work they did, because the work that they were doing was dealing with gamma rays, which went through their cells and messed up the DNA and messed up everything inside them, like causing cancer and radiation poisoning and other painful things. But lead or concrete can stop it. And that's why when you have x-rays with the dentist, they put that lead vest over top of you to stop the x-rays, right? And x-rays, again, are a different type. X-rays are larger than your gamma rays. All right, so these types of radiation have different amounts of energy and are capable of penetrating materials in different ways. So alpha particles, those can be stopped by your skin too. And then, of course, the other types, beta and gamma, can go through your skin, but they can be stopped by other things. So going back to the beta a little bit, this is definitely a little confusing because a positron is an anti-electron. It's basically an electron with a plus charge instead of a negative. We're not going to focus on there, but it is important that you know that there are 3 different things that can be released. So the first one is the alpha emission, which is like a helium nucleus, 2 protons, 2 neutrons. You can have a beta emission and the gamma emission. So this, make sure you write down. So if you had an atom like uranium and it's breaking down into different elements, then there's a process that it goes through. So naturally, over time, uranium's going to decay, but it's not like it takes a minute or even a couple days or a year. This takes a long time. So uranium's naturally going to decay over, look at this, not hundreds, thousands, millions, billions of years. 4,500,332,612 years. Okay? Uranium-238 decays into lead. So it takes about 4.5 billion years for uranium just to change into thorium. And then 24.5 days later, it becomes protactinium. And then a minute later, it becomes uranium-234. So when they decay into different elements, it doesn't all happen at the same amount of time, and some takes a really super insanely long time, and some are really quick. And then once you have uranium-234, it takes another 233,000 years to become thorium-230. So it was thorium with a mass of 234. Now it becomes thorium with a mass of 230. So another 83,000 years, and it becomes radium. Another 1,500 years, it becomes radon. 4 days, it becomes polonium. 3 minutes, it becomes lead-214. So it becomes lead with a mass of 214, but if you see, it's going to end up with lead as 206, so it's going to end up with 8 less neutrons than it had here. 27 minutes later, it's bismuth. 20 minutes later, it's polonium-214, not to be confused with polonium-218, which has 4 more neutrons because it's heavier. And then you got to wait another 1,500 years before it becomes lead-210, 22 years to become bismuth-210, then 5 days to become polonium-210, then 140 days to become lead-206. Once it's lead-206, it stays there. It's stable. So all this needs to happen. And so you can see, you start with uranium and it kind of bounces around and eventually, finally, it becomes stable. So there's a lot of different steps, and it depends on your ratio of protons to neutrons, if you're giving off protons or beta particles, or if it decays as neutrons and positrons, or just the beta emissions. You don't have to know which is which, but go ahead and hit pause and read it if you find this interesting. So different elements decay at different rates or speeds, and again, they give off different things, different one of these 3 things, depending on where they're at in the process. So here is our last slide. Unstable nuclei decay by giving off radiation. So if I run out of time, just make sure you pause and you read through this. Radioactivity is caused by the decay of the nucleus. It occurs when unstable nuclei lose protons or neutrons in those 3 forms of radiation: alpha emission, beta emissions, gamma emissions. So have all this on your notes. Nuclei are unstable when there are a relatively high number of protons per neutron. Unstable nuclei decay to stable ones by giving off radiation, which is particles, energy, and or heat. Radioactive emissions